Hello to everyone. My name is Matteo Centia from the University of Dundee, and I'm going to present the paper titled Numerical Assessment of Sinkhole-Induced Damage to Buildings. In the last century, the number of sinkholes in the southern part of Italy has dramatically increased, as you can see in this slide. In fact, back in 2013, this was the motivation of my PhD study at the Polytechnic of Milan. The objectives of my research were basically to answer to the questions that you see appearing on the slides. So what are the mechanism and controlling variables? Can I model such phenomena? Can I predict the lifetime of a geostructure, such as the formation of a sinkhole, or determine the time evolving factor of safety? And to answer to these questions, experiments, a numerical constitutive model was performed, and numerical modeling to give engineering answers was also performed. The starting point was that we knew that the dry and saturated strength were very different. Also, the stiffness would decrease with saturation, and that in the long term, we would also have the decrease in strength with time. The question, so why was this happening, motivated an extensive experimental campaign, and thanks to micro investigations, weathering mechanisms were identified. In particular, SEM images, X-ray CT scans of the soft rock, thin sections, XRPD to identify the calcium carbonate composition of the rock, MIP and 2D image analysis for the pore radius distribution, and SCM and thin sections of the intact rock and progressively damaged rock were performed. And all these micro investigations led to identify two things. First, the existence of two types of calcite bonds, the positional, as you see on the left, and the diagenetic on the right. And then three elementary weathering mechanisms. The short-term debonding affecting the positional bonds, whereby upon water saturation, the positional bonds would fall into suspension in the pore space. And then in the long term, with prolonged interaction with the water, the diagenetic bonds could dissolve and become thinner, so decreasing the strength of the rock. And finally, even more prolonged contact with pore water fluid, grain dissolution process could evolve. So these three elementary weathering mechanisms could be interpreted within a constitutive model. So this theoretical interpretation, basically, if you have in mind the yield locus, for example, a modified CAM clay, would shrink because of water saturation due to the short-term debonding mechanism. In the long term, as the water saturation stayed equal to 1, then we have the long-term debonding evolving and further shrinkage of the yield locus. This theoretical interpretation was then developed into a strain hardening plasticity model where we see the STD, the LTD, and the grain dissolution processes directly embedded into the constitutive relationship. The constitutive model was then implemented in an open source finite element code, allowing us to simulate boundary value problems such as a building over an abandoned mine, as you see here on the right. So how to calibrate the model? Well, you need uncoupled experiments where you test the material either in dry or saturated conditions or at different levels of pre-weathered states. Then you can validate the model by performing coupled experiments such as the soft odometer tests in where an acidic flow is subject to the sample through the bottom, and we can then measure the out pH and the settlement of the sample because of weathering. More details can be found in the mentioned papers. And then the model was then used to simulate the factor of safety of a building on an abandoned mine in this calcium carbonate soft rock. We calibrated the model as described in the previous slide, and then performed some model simulations to see its performance in, for example, predicting the shallow footing capacity of, and we also were happy about the the good fit of the results, and also that the model was able to capture the plastic bulb below the shallow footing as reported here in the slide. You can see the plastic bulb dimension was very was captured well by the numerical model. And at this point, we could imagine a weathering mechanism or a weathering scenario whereby we have a slightly acidic boundary condition imposed at the surface of our cavity, and this diffuses with time, damaging the rock. So we see that the rock is dissolved with time, decreasing its strength until failure is attained at the partition wall. Now, at the ultimate limit state, we could then define a factor of safety at different time intervals. So at the beginning, we do a CFI reduction and we can get the factor of safety. We can repeat this exercise at different levels of weathering states, so at different times, and get the different factor of safety. If we continue this process for various times, we can end up with a factor of safety dependent on time at the ultimate state. On the other hand, we can also use Boscardin and Cordin abaci and basically numerically calculate the angular distortion under a building and use this to define a new factor of safety at in service conditions. Basically, if we have the angular distortion, for example, below this part of our building, we can define the factor of safety as the distance OB, so the distance from the origin to the very severe scenario over OA, which is the current state, and do numerical simulations whereby the factor of safety will evolve because of the surface settlement and angular distortions until the factor of safety is 1. So in this short presentation, I showed you how these 4 initial questions could be answered thanks to an extensive experimental campaign, an advanced strain hardening plasticity model, and finite element modeling with reactive transport to define this new factor of safety at the ultimate and in-service states. With this, I thank you for your attention.